Okay, picture an exam hall. The clock is literally ticking down, and you can just feel the tension building in the room. We're looking at a real Cambridge physics past paper question, specifically from syllabus code 0625. Now, consider a student. Let's call him Alex. Alex is incredibly smart, right? But under pressure, he panics. He just overloads the page with raw physics facts. Every equation, every memorized definition about space, just thrown onto the paper without any actual analysis. Then contrast him with Sam. Sam is rushing. He barely glances at the question, completely misses the specific command word requirements, and writes this really brief, super generic response. Well, examiners report time and time again that the astrophysics section specifically concerning the Earth, the Moon, and the Sun is actually one of the most misunderstood areas in physics. And it's not because the physics itself is impossible. No, it's because students lack the structure to convey what they actually know. So today we are going to unlock the precise, step-by-step strategies that senior examiners are actively looking for when grading these questions. By the end of this explainer, you're going to know exactly how to turn those structural flaws into perfect scores. Let's get into it. Here is our roadmap for today. First, the cosmic clockwork. Second, the method mark strategy. Third, top examiner traps. And finally, the deconstruct, solve, evaluate framework. Section 1, the cosmic clockwork. Let's look at the core concepts. So, to fix structural flaws in your exam answers, your theoretical foundation absolutely must be flawless. Instead of just memorizing isolated facts, we need to visualize this as a deeply interconnected system. It's like a giant cosmic puzzle. Using this visual timeline, we can actually encode 3 essential temporal cycles into your memory. This isn't just about rote learning numbers, it's about understanding how each specific movement creates a distinct observable effect right here from our perspective on Earth. First up, the 24-hour cycle. The Earth rotates on its tilted axis once in approximately 24 hours. This spinning motion explains the apparent daily motion of the sun across our sky, which gives us our fundamental day and night cycle. Notice the key word there, apparent? The sun isn't actually moving across the sky. We are the ones rotating. Next, we have the 1-month cycle. The moon orbits the Earth once in approximately 1 month. This specific orbital journey changes the angle of sunlight reflecting off the moon toward Earth, and that explains the lunar phases, from a new moon all the way to a full moon and back again. Finally, the 365-day cycle. The Earth orbits the sun once in approximately 365 days. But here's the kicker. It's not just the orbit that matters. It's the fact that the Earth maintains that tilted axis throughout the entire orbit. That tilt, combined with the yearly journey around the sun, is exactly what explains our seasons. If you can just visualize these 3 distinct gears turning together, think of it like a spinning top being circled by a marble, while the whole shebang travels around a massive central sphere. You have the foundation to answer any conceptual question they can possibly throw at you. Now, this brings us to a critical distinction, and honestly, this is where so many students immediately lose marks. Rotation versus orbit. Rotation is spinning in place on an axis. Orbit is traveling a path around another body in space. Mixing up these two terms is literally the most common conceptual mistake students make right out of the gate. Seriously. When the command word asks you to explain the day and night cycle, and you write that the Earth orbits the sun every 24 hours, you have instantly lost the mark. No way around it, even if the rest of your physics is solid. Terminology really matters here. Okay, now that we have the physics vocabulary locked in, we need to talk about how you actually apply it to get maximum points. Section 2, the method mark strategy. Process over answer. Let's break down the actual mechanics of the exam itself across the 3 distinct cognitive domains that examiners are targeting. You see, the assessment framework prioritizes analytical depth over superficial breadth. First, we have knowledge and understanding, where the expectation is just that you state fundamental principles. This is exactly where our student Alex got stuck. He possessed the knowledge but totally failed to move past this basic domain. Second is application. Can you transfer these concepts to completely unfamiliar contexts? Like, if they give you a fictional planet with a 40-hour rotation and a 500-day orbit, can you apply the rules of Earth's cosmic clockwork to this brand new scenario? Third, and absolutely crucial for top marks, is analysis. Here, you must extract data, interpret relationships, and provide logical reasoning. And this is exactly where the Peel framework comes in. You might know it. Point, evidence, explanation, link. Top students make a clear point, they provide evidence from the data given, they offer a scientific explanation using fundamental physics principles, and then, this is key, they link it back to the specific context of the question. If you only provide knowledge without this structured application and analysis, you are leaving more than half the marks sitting right there on the table. So, the real game changer is mastering what Cambridge calls cross-topic connections. Basically, this is the ability to link fundamental principles across different syllabus areas to demonstrate a connected, conceptual understanding. Top-performing students achieve significantly higher marks because they literally prove they can transfer these astrophysical concepts into entirely unfamiliar contexts. They don't just talk about the Earth's orbit, they link the gravitational pull of the sun to circular motion principles, or they relate the varying intensity of sunlight during different seasons to energy transfer and thermal physics. Think back to Alex and Sam for a second. When we apply that Peel framework and truly decode the required connections, we see a massive transformation. Alex learns to filter that chaotic brain dump of facts into a targeted, analytical explanation. And Sam? Sam learns to slow down, read the command words, and provide the required depth.
Section 3. Top examiner traps. Avoid these mistakes. Now we're pivoting to the principal examiner reports to reveal the exact pitfalls where students unnecessarily lose points year after year. These reports, they are absolute gold mines of information, and they repeatedly highlight the same fatal errors. Read this quote on the screen carefully. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. Consider this a massive examiner alert. Merely reciting memorized space facts without applying them to the specific scenario guarantees a low score. For example, if the question gives you a data table about the temperature on different hemispheres of a newly discovered exoplanet, and your answer is just a generic paragraph about Earth's 365-day orbit, 0 marks. Imagine a complex data table showing the orbital and rotational periods of 4 different moons around a gas giant. Your job under exam conditions isn't to read every single number, it's to extract the core trend. Does a longer orbital distance correlate with a longer orbital period? You have to scan, extract, and apply.
Let's look at a few more specific mistakes highlighted in those examiner reports. Using the wrong approach for the wrong context, forgetting correct format and presentation, omitting clear headings and correct terminology. Let's say a student writes something like, "The planet gets hot because it moves closer to the sun during its spin." Okay, spot the flaws. First, they use the word spin instead of rotation or orbit. So, wrong terminology. Second, they attributed seasons to the distance from the sun rather than the tilted axis. Completely the wrong approach. Poor presentation and a lack of clear annotation will just obscure an otherwise solid understanding of the physics. And examiners cannot and will not give you the benefit of the doubt. If the terminology is wrong, the physics is wrong. Presentation of information follows strict conventions, meaning you must use proper headings, correct formats, and show clear, unambiguous working.
Section 4. Deconstruct and solve. Evaluate effectively.
Okay, picture this. You have only minutes left on the clock. How do you write a perfect paragraph? You need a standardized sequence. You cannot just stare at the blank page waiting for inspiration to strike. You need a machine-like process that works every single time, whether the question is about the moon's phases or the thermal capacity of a satellite. Walk through this specific 5-step sequence with me. Step 1, identify given information. Deconstruct the prompt. Highlight that command word. Circle the variables. Step 2, break into logical steps. Don't try to solve the whole thing at once. Plan your structure. Step 3, solve systematically. Execute your analysis with clear working. If there's math involved, show every single step. If it's a written explanation, use your specific terminology: rotation, orbit, tilted axis. Step 4, check for reasonableness. Ask yourself, does your answer actually make sense in the real world? Like, if you calculate that a planet's day is 0.002 seconds long, you've probably made a calculation error, right? Step 5, make justified recommendations or conclusions. This sequence integrates perfectly with your time management, moving systematically through these steps exactly the way an examiner wants to see it. It essentially forces you to show your method clearly and unambiguously. Finally, to secure those absolute top-tier marks, you must demonstrate evaluative thinking. What does that mean? It means you question assumptions, consider alternative interpretations, and identify limitations to justify your decisions with evidence. Evaluation of evidence quality requires you to step back and look at the whole picture. For instance, if an experiment measures the shadow of a stick to determine the Earth's rotation, an evaluative thinker is going to note the limitations of the measurement tools. They'll point out the assumptions made about the flatness of the local ground and explain how these factors might actually affect the final conclusion. This level of critical analysis, that's exactly what separates a good physics student from an elite scholar. So let's wrap up with a final thought. Are your answers telling a specific structured story, or are you just reciting generic space facts? I really want you to challenge yourself on your very next practice paper. Actually apply the deconstruct, solve, evaluate framework. Force yourself to use the Peel structure. Decode those command words before you even pick up your pen.
By internalizing these methodologies, you won't just be memorizing data anymore. You'll be communicating complex physical truths with absolute clarity. Keep practicing, stay structured, and I will see you in the next explainer.